Thank you very much, everyone, for coming. As was said before, we're going to be talking about some of the aspects of black holes and gravitational waves. And I've also, I have the pleasure of having Juan here with me, who's also going to talk a little bit more detail about gravitational waves. But before I get started, I just wanted to start where pretty much where it all began. And basically start with what we all know to be gravity. Okay, and gravity and Newton are more or less synonymous with each other. Newton was the person who realized that it was the same force that caused an apple to fall to the earth, and the force that keeps the earth orbiting around the sun. So that basically makes for the moon go around the earth, for the earth to go around the sun, and everything. And these were all the same forces. So if you will, everything that you see happening around you, from stars all the way to things falling to the earth, are all governed by the same force. And for those who are, who've done a little bit of mathematics, you can see the formula here below, where the force on the F on the left-hand side depends on the mass of one object, depends on the mass of the other object, divided by the distance between them squared. Okay, so that's the classical picture of gravity. And it wasn't until about 100 years ago when Einstein came along and revolutionized the idea of space-time. And in particular, in the old theory, in Newton's theory, it was not fully understood how gravity is transmitted. In other words, how does the Earth know about the presence of the sun? Or how does the apple know about the presence of the Earth? And that was a big open question that Einstein brought in. So in the Einsteinian field, gravity is nothing but the curvature of space-time. So here you see an image where I'm trying to illustrate this exact same thing. So here you see the Earth, and it's a big, massive object. And because of its mass, it's going to bend space-time in a particular way. Pretty much if you put if you tighten a piece of cloth and you put a marble on it, and you can see the cloth deforming. Now, if you put another marble in there, you'll see that both marbles are going towards each other. And that's exactly this notion of space-time that Einstein envisaged. And this is most succinctly summarized by a quote by John Wheeler, where it says that space-time tells matter how to move, and matter tells space-time how to curve. Okay, so there's really this interaction between matter, which curves space-time, but then the curvature of space-time dictates how matter moves and where it goes. And that's what we then here on Earth and everywhere else we perceive as this gravity force. Now, I'm not going to talk too much about gravity today, but I want to talk about one of the most elusive predictions of Einstein's theory. And in particular, it's the notion of a so-called black hole. Now, those of you who are in this lecture probably will have heard about this term called a black hole, right? It's very often used in popular science, and it's a term that is thrown around. But what is it really? Okay. Now, most commonly, people know this to be, this object, this cosmic vacuum cleaner, where it sucks so hard that not even light can escape. Okay. Particularly, there's this surface where there's no return. Another thing that people mostly associate with black holes is that it's extremely compact. So, for example, if I take the weight of Earth and I make it a black hole, then it's basically an object that would fit in the palm of my hands. That's how extremely compact an object like a black hole is. Now, I'll talk a little bit about the weight and the size of a black hole later on, but I just wanted to give you an impression that a black hole, if you make it a black hole the size of the weight of the sun, it would still fit well within Hong Kong. Okay, and finally, most people will associate this notion of a black hole with extreme space-time curvature. You can kind of see here on the bottom right, you can see the sun being something that curves, something like a neutron star that curves a little bit more, and a black hole is the most extreme way in which you can curve space-time. So these are the things that people typically associate with black holes. But today, I wanna bring the focus to a little bit to a different aspect, and I want to talk about what do we know about black holes, and why do we know what we think we know. So that's our journey that we're going to start off with. So let me just start by showing you a picture of a black hole. Okay, this is a black hole. As you can see, hopefully, you know, your screens are not broken. This is pitch black. This is the whole notion of a black hole, right? It's black. Now, of course, this is not necessarily the way we will see a real black hole. And in order to explain how black holes work, I want to take you on a short journey. And I want you to perhaps even close your eyes and imagine that we're on this spaceship and we're going towards a black hole. And when we get there, we're gonna slow down the spaceship and we're gonna just orbit around this black hole. Okay? Is everyone there? Orbiting around the black hole. So let's think about what we may be able to see. So the first thing that we may notice is that because the black hole has a particular mass, it's going to, by gravity, it's going to attract all this dust that is flying around in space, right? Space is very empty, but still there's a lot of dust going around, just tiny little particles. And we can see this black hole sucking in all these particles. Now, because of the way gravity works, when you're far away from the black hole, the gravitational force is going to be weak and the particles is going to move very slowly. And because of that, the particles are going to vibrate very slowly. Now, as we go closer and closer to the black hole, we're going to accelerate, we're going to increase the speed of these particles all the way down to the black hole. And so as we get closer and closer to the black hole, as you can see with these arrows, the closer you get to the black hole, the more energy, the more velocity, the more speed these particles pick up. And this speed has a consequence. And the consequence is that the temperature of all of this gas starts to heat up, right? The more particles, the more velocity they pick up, the hotter this whole gas becomes. And here I'm just showing you an image to illustrate what that means. So when you have very cold gas, it's going to emit something that is very low energy or very warm color, almost like reddish. And the more you heat up the gas around it, the more the color changes into almost like the blue spectrum of things, all the way down. And so as you go deeper to the center, this gas gets deeper to the center, the more blue the gas becomes. And so if you then look at the black hole, you see all the gas going in. One image that you can think about is that you can see this gas coming in, and it starts to go almost like a rainbow. It's almost starting from red hue, and you go deeper and deeper and all the way to very bright blue. That's the spectrum you're going to see. So a black hole may not necessarily be pitch black. There could be stuff around it that lights up and gives you a sense of light coming out. But what makes a black hole in particular special is that there's suddenly this edge. Suddenly, there's no more light, only darkness. And one way to think about this is what we actually call a horizon. So this is a typical image if you look out into the ocean. And you can see that, you can see the ocean, all the way at some point, you see this line and the ocean stops. You can't see any further. And this is what we in English call a horizon. And exactly the same thing happens for space-time. You can look out, and suddenly there seems to be this edge where you can't see anything anymore. And this is actually, this could be illustrated by this image here. This is a kind of a waterfall in a circle. And you can see the water. You can see the water until it suddenly drops into this abyss. and the water just goes down. And if you look through it, you can see the water, and suddenly there's no more water. There's this sharp edge that you see. And so going back to the black hole, right? This was the original starting image of a black hole. We see nothing. But now, if we now put in some background, okay? So behind the black hole, there may be stars lining up. And so now if there's stars in the background, we suddenly see this black hole as all the light from the different stars coming towards us, except for this sharp edge of a black hole. Everything, the light that would normally come to our eyes if the black hole wasn't there, suddenly all falls into this black hole. So the real image or an image of a black hole could be background light and then suddenly this black, well-defined edge. And that's what we call so-called black hole horizon. That makes a black hole so special. Okay, so now we do a different experiment. Let's say we want to know what the mass of a black hole is. So what do we do? So we're in our spaceship, and now, instead of looking directly at the black hole, we are going to orbit the black hole, just like the Earth is orbiting the sun. And we're going to do two things. One is, because we know how the spaceship travels, we're going to very carefully measure the distance that we travel to make one circle, to make one orbit. Okay, and we're just going to note down the amount of distance that it takes us. Like, how big is this circle if we orbit the black hole? And we're going to do a second thing. We're also going to time it. We're going to take our watch and we're going to time the amount of time it takes to go around the black hole once. And with these two pieces of information alone, right, just the amount of distance it takes for us to make an orbit and the amount of time it takes for us to make an orbit, we can use a simple formula. And this doesn't even come from Einstein's physics. This could come from Newtonian physics, where on the left-hand side, we have the period, the amount of time it takes for us to go around the black hole, squared. And on the right-hand side, we have the orbital radius, or basically the size of our orbit. And then we see below the line, we see the mass of the black hole plus our own mass. Now, of course, we know our own mass. So we can infer the mass of a black hole. We can know how heavy a black hole is just by going around it and measuring these two quantities, the period and the orbital size. So when we have the mass, we know the mass, we also know something else. We can play a little bit like detective. So if you imagine that, the way we know that dinosaurs exist is by looking at the fossils of dinosaurs or by digging up its bones. And in a very similar way, we can learn about what happened before the existence of these black holes. What created these black holes? And in our themselves. The way to think about this is that the star becomes so heavy that basically nothing can stop it. Nothing can stop the gravity from pulling it inwards very tightly. Now, if you do that enough, if you compress the star enough by this implosion, you're going to get a so-called supernova explosion. So that is something that goes outwards. And then what you leave in the middle is indeed this black hole. Now, because in this explosion, we only lose very little of its mass, we pretty much know that the size of the black hole, the weight of the black hole, must have been about the same weight as the star that it started off with. So not only can we learn something about the black hole, we can also know about, if you will, the dinosaurs, just by looking at the black hole and knowing that a star must have exploded in order for it to be formed. Right? So we have many pieces of information now that we can gather around from the black hole. We can take a look at the black hole. We can look at its horizon. We can measure its weight by going around in orbit. And we can even now learn something about the star that exploded in order to form this black hole. Now let's go another step further. Okay, now these supernovae have actually been seen before. This is not something that we have envisaged just by pure science. If you look at it, this is an image of what we call the Crab Nebula. And this is actually like millions of years ago. There was a stellar explosion that caused this, all these dust to fly around. This is an actual image of what we call the Crab Nebula. This is all this dust that is now flying around in space because of the explosion of the star. Okay. Now we now know that there was a star before the black hole, and we can learn even more. If we even look at our own sun, which is believed to be a star, then we know that our sun is rotating. Okay, and if you actually do a careful study, you even know that, you know, around the north pole of the sun, it rotates faster, and around the equator, it rotates slower. And this is something we can actually measure, right? We can make images of our sun, and we can look at how fast it rotates. Now, just as that the mass of the original star didn't drop that much, didn't lose that much mass in the explosion, we also know that all of this rotation cannot be lost simply. And so if the star was rotating before the explosion, we know that whatever is left, in this case the black hole, must also be rotating. So we now also think that, you know, a black hole is not just this object that stands there in space, it also rotates. Now, what does that mean? Like, if a black hole rotates, what does that mean? Because it's just this black thing, right? What does it mean? You can't take a picture of something rotating. But remember the gas that I talked about, the gas that, you know, surrounds a black hole and actually makes a black hole visible to us. Well, if a black hole rotates, what it does is it causes space-time to rotate with it. If you will, it's like a vortex. Like the black hole is rotating and it's causing space-time to rotate alongside with it. And in technical jargon, this is called frame dragging, right? The whole frame, if you can see this in green, that's space-time, and space-time gets dragged around like a vortex around the black hole. And as a consequence, everything around it, all the matter around it, must be dragged alongside with the rotating black hole. And so if we now look back at this matter that falls in, not only do we see the matter just going in towards the center of the black hole, but we also expect to see this rotating around the black hole. You can see this disk orbiting around this black hole. So just by looking at the gas and see how the gas falls into the black hole, can we also learn something about how fast the black hole is spinning? So that's another piece of information just by looking at the gas of the black hole. So we're starting to get a picture now where we can get the, we can look at the gas to get, you know, we can look at our own orbits, we can now get the mass, we can get how fast it's spinning, we can get all of these interesting pieces of information about a black hole. And then slowly we're starting to piece together all of these pieces of the puzzle. Okay, now what about the size of a black hole? I mentioned earlier the so-called event horizon, the sharp edge where light does not even penetrate. And so you can see the sharp edge, but where is this sharp edge? Now, in order to answer this question, we need to turn to Einstein's theories. And if we do the calculations in Einstein's theories, we arrive at a simple relationship that the more heavy the black hole is, the bigger its size. And by this case, by the size, I mean, where is the event horizon and how far is it away from the center? So you can see this formula over here in the middle, where the radius of a black hole is just proportional to the mass of a black hole. So let's go back to the earlier comment that I made. And let's think about the size of a black hole. Let's see if I can give you a sense of the size. So I told you before that if I put all of the weight, so everything, everyone on planet Earth, and I make them into a black hole, I get something of the size of a marble, something that could fit in my hands. That's the size of a black hole if I put the entire Earth's weight in there. Similarly, if I put the weight of the sun in the black hole, or if I turn it into a black hole, then this the size of this will become something, the size of Hong Kong, right? Not even 10 kilometers. So imagine the entire weight of the sun all inside Hong Kong. So if you think you're living in a crowded situation, trust me that, in a black hole, everything is much more dense. But that's not the end, right? That's the sun. We even know that there are, out there in the universe, there are black holes that are many, many times bigger, many times heavier than our own sun. Here on the bottom left, starting at the bottom left all the way to the top right, we can see different black holes that we know or that we think must exist. So even at the bottom left, we see NGC 1277, and that's 5 billion times the mass of the sun. And then all the way to 18 trillion times the mass of the sun. And all of these will have a different size for the black hole. Now, to give you a better sense of how big these black holes are, I'm going to take the black hole here on the bottom left, right, the 5 billion times heavier than the sun black hole, and I'm going to project this onto what we do know. So in this tiny dot in the middle, okay, you may have to wipe off your screen to see that dot. That's the Earth's orbit, not the size of the Earth, but that's the Earth's orbit around the sun. Okay, now it's so small you can't actually see it. So now the next ring, the blue ring, is Neptune's orbit. Okay, so this is the orbital size of Neptune, and basically this is the size of the solar system. And then all around it, here in black, you can see the size of the black hole, which is 5 billion times heavier than the sun. It is many, many times bigger than the entire solar system together. Okay, so black holes really do come from all sizes and all weights, and they could literally, be as big as many, many times our own solar system. Okay, now why or how do we know that black holes exist? And this is an interesting question because black holes are black. We can't point a telescope there and maybe see its gas. It's very difficult to do so. But there are ways in which we can study the existence of black holes and even the properties of black holes. So one thing that we can do is we can actually follow stars for many, many years. And let me show you a video. Sorry, let me just show you a video of looking at these stellar orbits. Here we see stars going around what seems to be something very heavy. Okay, and we trace these stars for many, many years, and we see them going around. Let me play this again. Right, you can see all these stars moving, and somehow they seem to be moving around one single object, a very, very heavy object. I'm going to just pause it right here. And the thing is that if we look at this spot, and for those who are interested, this spot is actually the center of our Milky Way. If we look at the center of our Milky Way, we see nothing. With a regular telescope, we see nothing there. We know something is there, something very heavy is there because we see all the different stars going around it. But we see nothing there. And the only explanation is that there's a very heavy black hole right there in the center. Now that's more or less an indirect evidence. And very recently, an experiment called the Event Horizon Telescope has managed to actually make what we call a picture of a black hole. Now this is not really directly a picture of a black hole. It's more like the shadow of a black hole. We look at a particular part of the sky where we think there's a black hole, and we look at the light source, and we see that suddenly there's this hole in the middle. And this hole in the middle is what we believe to be a black hole. Okay, so this is an actual image of a black hole that you can make. Now, these are two pieces of science that we can do, observations that we can do to infer the existence and the properties of black holes. Now, there is a third way of doing it. And for this, I'm going to now turn the microphone over to Juan, who's going to talk about a very exciting way to measure the properties of black holes. Okay, so let me give the mic to Juan.
Okay, does people see my messy screen?
Okay.
Okay, so now I'm gonna turn to my presentation. Does people see my presentation? So I'm gonna turn into play mode to make it big. Perfect. So, sorry for these 2 minutes of technical problems. Another technical question. I'm gonna ask people to write in the chat at some point, okay? Because I like a lot to interact with the audience. We cannot hear today, but we have the chat. So let's try to use this tool. So as Professor Lee said, this is the most direct image from a black hole we have using light, okay? Since the beginning of history, humans have studied the universe using the light it emits. And that has made us learn a lot. We've discovered that planets also have moons. We've discovered that maybe other galaxies. And we have even made almost photos of the beginning of the universe. We have lots of stuff. But we cannot access the shape of a black hole, the border of a black hole, just with light. In order to do that, we need another tool that we call gravitational waves. So to understand what are gravitational waves, let's get back to the picture of what gravity really is. So Professor Lee mentioned to you that space and time, so space is not that kind of dead thing in which things happen as time passes, right? Time and space are something that are tied together, and they are not dead. They react to what things do on them. In particular, as we said before, when we put something on that space bends. And because that space bends, then things on it start to move in a certain way, as John Wheeler said with this quote. So Professor Lee talked about black holes, which are things that curve this fabric, space-time fabric, in an extreme way. But the black holes he talked about, they are still standing there. The most they do is eating stuff. Now we're going to talk about black holes that are dancing around, okay? And let's see what happens to space-time. So black holes, sometimes these ones are yellow, but these are supposed to be black holes. Sometimes can get together and they start to move around. If you believe this thing that space-time is a fabric and that it gets bent when they put something on it, then if I start to move that thing around, it's kind of easy to understand that the space-time, so this fabric should tremble. And this kind of deformation should propagate away from the source that is creating that deformation, right? So this is what black holes do when they get into couples. It's pretty much like when we throw a stone on a pond. So when we throw a stone, we create a kind of blob, and then this blob starts to propagate around in the form of waves. So when this happens in space-time, we will talk about gravitational waves, not water waves. So this is the picture of a black hole that Professor Lee showed before, just that we have put two together now. And of course, we have put a background of stars so that you can see the actual holes. Otherwise, you would see only black. And now these black holes start to move. Because they move, they are emitting these gravitational waves, although you don't see them here. And because they emit these gravitational waves, they lose energy. And the consequence is that they approach each other and collide and form this single black hole. So in this process that you saw in terms of light just before, now I'm showing the waves. So you have the two black holes orbiting each other. They create this disturbance in the fabric of space-time. This disturbance is larger and larger until they collide. And now these waves are going to travel around the universe. There is nothing that can stop them. So they travel, they deform everything. They travel for many, many years. We will see how many later. And at some point, they can reach Earth. So when they reach Earth, they will squash it and compress it, not as much as I show here. This is very exaggerated, but they will create this effect. And we have detectors that can see this effect. And from that, we can try to infer what created these waves. So what these black holes were and what they were doing. So we use a kind of telescope to detect these waves. And our telescope is not a telescope in the traditional way. We have this really big thing, which is composed by two arms. These arms are 4 kilometers long, and this one is placed in the US. So inside these arms, we have lasers. And these lasers get thrown, they get reflected in two mirrors, and they recombine here at the center. Now, oops, I should stop the video. Let's repeat. We have these two arms. In these two arms, we shoot two lasers, okay? These get reflected and come back. They recombine at the center of the image, and now something will propagate. The result of that combination will propagate to the mirror on the bottom. So you see that that mirror is receiving this intermittent light. Now, these lasers, these arms are configured in a very particular way. We place these arms and these lasers so that if nothing is going on in the detector, if no gravitational wave comes, when these two lasers recombine, they kill each other. You know, lasers can kill each other. So we see no light at our output. But now if a gravitational wave comes, these two arms are going to start to tremble. So they will become larger and shorter alternatively. And you will see that we will receive a pattern of light and no light. And because of this pattern, we can know if we are seeing a gravitational wave or not. And furthermore, we can know what created it. So let's look again at the waves from our black holes. But now we're going to look also at the light pattern that we expect from these black holes. And this is shown on the bottom, is this curvy thing that you see here. Okay, so let's play it. So as before, you have the two black holes orbiting. At the beginning, they create very tiny gravitational waves, and you see them here on the bottom. And now when the two black holes approach each other, they are going to start to accelerate. They create like stronger and stronger waves until the point they collide. And when they collide, you will see an enormous peak of gravitational waves. I'm playing it really slow now. You see? This grows, grows, grows. And now when the two black holes merge, you have these enormous peaks of gravitational waves, which you see here on the bottom. And then we are left with a final black hole that relaxes, losing any kind of defects it may have from his birth. It's pretty much like a baby. When it's born, it's still crying a bit, but then it shuts down eventually when it relaxes. So how do we detect these gravitational waves? So first question in the chat. How many of you know the Shazam app? And I cannot read the chat, fantastic. So Professor Lee will tell me if someone answers.
No one is answering.
No one knows Shazam.
Yes.
No, someone knows Shazam. So Shazam is an app that we put on our phones to identify music. So the way it works is we are in a disco. This is in my hometown in Spain. And some music that you like, but you don't know the name, it's being played. And you wonder, what's the name of this music? Who's singing? So you take your app, the app records the sound, it compares that sound to a database of songs, and it says, oh, the most similar is this one here. Of course, because this is in Spain, the song was reggaeton. Now, we do a similar thing, but our club, our disco is the whole universe. Our phone is 4 kilometers long. our database is of black hole songs, the waves that these black holes are creating when they are orbiting. And at the end of the day, our phone app tells us, oh, it was two black holes that look to have the same size. Who created this? So the next question is, how do we know what those black holes were just looking at the music, at the gravitational waves they were playing? So who does this, first of all? So here I want to mention the LIGO scientific collaboration, in which both Professor Lee and I work for many years now, more than I would like to, because that means I'm old. And so we basically have two detectors in the US. They are separated by 3,000 kilometers, and one extra detector in Italy, in Pisa, where the inclined tower is. And there are lots of universities in the world dedicated to this. And this collaboration has more than 1,000 members dedicated to just look at these waves and learn what these black holes were doing. So once again, I present you with a black hole. And you see nothing because it's black and we don't have nothing on its background. It looks like this. And then, so now I'm gonna show the first signal we detected. We analyzed data from these detectors for years. We never detect anything. And suddenly one day we get something like this. The two detectors we had record these two signals. On the bottom of the two images, you see the curvy line that I was showing you. This is a gravitational wave. You see that both signals are the same. So both detectors saw the same. And then you see on the top, this kind of curve, this bright curve. We will discuss that later. We call that a chirp, okay? Just like what the birds do. So what happened here? What produced this signal? So we learned many spectacular things about it. First of all, this thing was really far away. It was 1.3 billion light years away. It's very complicated to get a sense of what this number is. So the way to understand what this number means is these waves have to travel for a lot of time before they reach us. So this 1.3 billion light years means that it took for them 1.3 billion years to get to us. It means that when these two black holes collided, life was starting to thrive here on Earth. No dinosaurs, no people, no anything, just microbes. Okay, so really long ago. And this signal reached us now, 4 years ago. This was produced by two black holes of around 30 times the sum of the mass that collided. So let's get a sense of how spectacular these numbers is. You need to get 30 suns. You need to squeeze them into the size of Hong Kong, more or less. This is one black hole. You do the same and create another black hole. And then you make them collide at a speed that's close to that of light. So all of those numbers are enormous. So this event must be really catastrophic. It's so catastrophic that if you could get the gravitational waves that were produced and put them in light, this thing would be brighter than the whole universe that you can see together. Okay, this thing would be outstanding. These events are real cosmic catastrophes. So now that we know that black holes can produce gravitational waves, let's look at the 10 gravitational waves we have observed so far. So these are all of them. And only looking at these signals, it might seem that we cannot learn much about them, but we can. And we're gonna do here the course Black Holes 101, okay? So first thing, a short signal means that the two black holes that collided were heavy. And if the signal is very big, so very loud, it means that they were nearby, okay? So the first question I'm gonna ask to people is, can anyone guess which are the two heaviest black holes here? Remember, heavy means short. So if people can answer in the chat with one of these numbers that you see in top of the waves. Can you guess which is the heaviest one or the two heaviest ones? Is anyone answering?
Not yet. Let's wait a second.
You can tell me the left column, the middle columns, the right column, or just the name of the wave? Okay, someone answer.
Yeah. 15, 12, 26, and 17, 06, 08.
No. So the two shortest ones, I think, are these two. And actually, I know are the heaviest ones. So just looking at the waves, you can see that these are the two heaviest ones because they are the shortest ones. So it's the ones for which you see the least number of wiggles, of cycles. Now, remember that loud, so big, means nearby. So out of these two, the two that I have in my circle, which one do you think was closer to us? Top or bottom? So people, please answer. So people saying? Top. Okay, so you got it right. The top one is nearby, and the other one is much more far away. Okay, so next question. Remember that the better you can see the individual cycles, so the shorter the signal is, the heavier it is. So which ones do you think are the lightest? You can answer. Is anyone answering? So which one do you think is the lightest couple of black holes?
15, 12, 26, 15, 10, 12, 17, 06, 08.
Okay, so
17, 06, 08.
yeah, so people have got it. So these two are the lightest ones. It's the ones for which you can basically not see the individual wiggles. Okay, good. So this is black holes 101. So apart from deciding what are the masses of these things and how far they are, we can do way more fancy stuff. So we can localize them in the sky. So for each of these signals, we can infer where in the sky we think they are. Now, remember, or I should tell you, these detectors work like ears, okay? So you know where someone that is talking to you is because you receive the noise by both ears and then you can localize it. Here, for most of our detections, we had two detectors working, the two in the US. So that's why you see some really large blobs on the sky. We don't really know very well where those things were, but we have two that are very well localized. And this is because our third detector was working. So you can see that with a third detector, we can squeeze where we think the source was, so the two black holes were, and we can say, okay, the black hole was there, and now people can turn telescopes and try to see them if something comes out in light. So I showed you these signals, this kind of wiggle, but I didn't show you what's going on. I showed you what's going on, but I didn't explain it in detail what's going on in each of the part of the signal. So the signal itself allows us as well to know what's going on with these two black holes that are going around each other. So we have a first part that we call in spiral, which is when the two black holes are slowly orbiting each other and falling down into each other, which is the first step. So what you see is a signal of constant frequency. This is like a constant tone of music. And after this happens, you see that the two black holes eventually collide. When they collide, remember, there is this big burst of gravitational waves that we can see here in the end of this kind of chirp. And then at the end, we are left with a black hole that is deformed, is like too bothered, and it's emitting gravitational waves, getting rid of all of its defects until it becomes like what Professor Lee showed, a spherical black hole that has a smooth surface. So this last part we call ring down, and this ring down allows us to study really, really cool and fancy properties of these black holes. Why is this? So this is because of the following. The first part of the spiral allows us to infer the two masses of the black holes. So you can see here a plot that we made in our collaboration with all of the signals we have detected, those 10 bananas if you want, and what we think the two individual black holes were, the masses. Now from the end of the signal, what we can learn is what's the mass of the final object and how fast it's spinning. These are the two properties of the black hole that Professor Lee has been discussing a lot in the last half an hour, right? Mass and how fast it's rotating. Now, I mostly care about that last chop. So the emission produced when the final black hole has formed is really, really like distorted and it's trying to settle down to its final form. And why is this? So this is because if you imagine space-time as if it was water, at the beginning we can think that this water is having like tiny waves. So these are calm waters. So we cannot learn much about what water can do if it's just calm. At the end, we have like the worst space-time storms that we can see. And as you can see in movies, these storms are the only way you can see water really making strong waves and stuff that you will never see if you were on a pond, right? So I'm interested about these space-time storms. So what we can learn about that? So there is a very fancy property of black holes that we can study. And how many of you think a black hole is something really complicated and really mysterious? Just say me or Jess in the chat. Because black holes are something like people think they are super complicated. And people are not answering much. So there's someone that says that it's really complicated. So it turns out they are not. A black hole is something really big, really mysterious, but if you know the mass and the spin of that black hole, so how big it is and how fast it rotates, you know absolutely everything about the black hole. This is said as black holes have no hair. So there is just that ball. And this is, for instance, not like in a bathtub. So on the right hand, you have a bath. And typically you would say, if I know the temperature of the water and how much water I have, I know everything about my bath, right? But that's not completely true. There are lots of tiny water atoms, oxygen and hydrogen doing their own stuff that will determine what that water is really doing. That does not happen in the black hole. So looking at that late emission that I said before, that tiny, tiny moment in which the final black hole has formed, we can study whether black holes are complicated or not, like I'm saying here. So I'm gonna talk about a different thing though. I'm gonna talk about trying to know what the shape of a black hole is, which is the title of this talk. So for that, let's recap what's going on in this binary. And let's go back to that mysterious chirpy thing that I showed some slides before. So I've already presented you the gravitational wave signal that you see on the bottom is this wiggle, and you already know what's happening there. First, the two black holes approach, then they collide, and then the final black hole relaxes. But now let's see what happens to the frequency of that signal as the time evolves, okay? So you have here a first part in which the frequency just goes slowly up. So this is like a music going from low tone to high tone very slowly, like, okay? And what this is telling us is that the speed at which these two black holes orbit is increasing. Then we have the merger. At the merger, we have this super high tone. So the whole signal has done something like, okay? And then at the end, we have the ring down. So what can we learn from here? It seems that the signals are really simple. So if all of the signals that we've seen so far look like what I just showed you, okay? These are the 10 signals we've seen so far. And you can see that all of them show the same kind of curve, which is in the bottom of every panel. And all of them show this single chirpy track, okay? So this is telling us that these are two black holes orbiting and smashing each other. There is one here that is way longer than the other ones, which is the one on the bottom. That thing, because it's really long, can people tell me if this is something heavy or light? What do people think? The thing on the bottom of right, the really long thing. Is people answering? Is that heavy or is that light?
Light.
Okay, everyone thinks that's light. And that's true, because these are not actually black holes. These are two neutron stars that are things that are way heavier than black holes that collided with each other. So even from this kind of simple thing, we can know whether the two things that collided were black holes or neutron stars. So, okay, let's look at black hole signals. We can simulate black holes with computers and look at the signals we expect from them. So we have got a computer, we have simulated a black hole collision, and we have looked at the signals. So all of the signals that I showed you before have many things in common, but one in particular, and it's that we are seeing the collision from the top of the collision. So the two black holes are here, and we are here on the top, seeing that collision. So that's the signal you see here. You are the koala, and you are on the top of the collision, and you see the signal I've shown you, okay? Next, let's move to the edge. So now you are on the plane of the collision. You are not on the top, you are on the side. And let's see what the computer says we should see. And you start to see that the signal, well, is similar to the previous one, but not that much. So let's try another location on that plane. And you see that something starts to pop out here on the right. So on the left of this picture, you see the track that I've shown you before, and then you see something else. So if we move the koala to another position, then we clearly see that we're seeing two chirps. So the first chirp comes, and then a second one. But there is something even more mysterious, which is the fact that the final black hole is forming when the bottom axis is at 0. I think I cannot move my arrow here. What happens if I escape? Perfect, I can do this. So the final black hole has formed here, okay? So there is nothing orbiting. We were saying that the frequency of this grows because there are stuff that is orbiting and is accelerating. But here we don't have we don't have an orbit anymore. We have a final black hole. So what's going on here, right? So Einstein on the top of the picture is freaking out and he's saying, I didn't know this could happen. What's going on? So he will have to check what these black holes are doing. And we can have a look to what our black holes are doing in our computer simulations. So I present you with Chris Evans. This is a student in Atlanta, in Georgia Tech, and he made this simulation, okay? And what you're gonna see here is the two black holes, which are the two circles that you see here, and they're gonna start to orbit, okay? And the color is the intensity of the gravitational waves. So let's look at the simulation. So you see that the two black holes start to orbit each other, and you see some emission. And those gravitational waves are basically uniform, right? The thing does not look very special. So let's wait a bit until the two black holes collide. Hopefully before 2021, because this is taking time. Okay, the two black holes are about to collide, and you can see that something starts to form here, right? This is forming here, and now when the two black holes collide, I'm gonna stop it a bit. Okay, I stop it. Now you see that there is a clear structure here. There are like 3 beams of gravitational waves in one side and just one on the other. So this black hole that has just formed is emitting more from the one side than from the other. And why is that happening? Okay. You see that now this rotates, and this pencil, this beam of gravitational waves is pointing to everyone, to every of the koalas we were placing before. And it's pointing to everyone. And these signals will reach all of the koalas. So now we see to those signals on the left, we look at those signals on the left. Once they have escaped the black hole and they are reaching all of those koalas that I was placing here around. And now imagine that I tell you that waves were exactly like sound. So each of these color lines is a bit of sound, okay? And the stronger, so the more often you get those beats, the higher the tone of the music will be, okay? So now you see that one of the observers, so the one on the bottom, is getting 2 of those sets of really fast beats, whereas the one on the top just gets 1. So I don't know if with this, someone can tell me which of these observers on the top or on the bottom will see those 2 chirps, those 2 things that I was showing before, bottom or top. LOL. I like the koala emoji. Top, bottom. Okay, I need more votes because we have 50-50. Top. Okay, so no, it's the one on the bottom. So the koala on the bottom is going to receive like so really fast sound beats one time and then another time. So that's gonna make the frequency of the noise of the sound rise once and then twice. So we have an explanation of why that happens now. What's going on in the black hole? So what I have on the right is the pictures of the black hole that has just formed, okay? And Professor Lee told you that a black hole is like a sphere, but I told you that when the black hole has just formed from the collision of 2 black holes, it's really distorted. And you can see that in the first of the images, that black hole has a peak, okay? It looks like a chestnut. It has like a flat back and a sharp peak on the top, or on the bottom in this case. So it's not a sphere. And then it loses that kind of shape. It becomes circular, it becomes spherical as it emits the waves. So that's telling us basically that the black hole is emitting more waves from the side in which it's more peaked. So that's telling us somewhat that if we look at these waves, we can know what the shape of this black hole is, right? And what I'm going to show you later is the only technical thing I'm going to show in this talk, which is what comes next. So here you can see the shape, the chestnut shape I just mentioned before. You see that kind of peak on the one side, that wide back on the other side. And you can see how there is more gravitational wave emission from that pinch, from that peak. And actually, if we try to put in a plot how curved that black hole is and how much is emitting from each point, you can see that the 2 things match. So this means soon we may be able to know what exactly the shape of a black hole is. And that's where I'm gonna close the talk. And if you want to ask questions, please go ahead.